Hello and welcome to this presentation where we'll review automated student advising in the context of the AutoScholar advisor system. First, some context. The system was created simply to automate the processing of complex rule sets relating to student registration and progression. It is being used to identify and predict which students are at risk of failing before failure actually occurs. It has been used in several institutions in South Africa and one in the US. Many of our partners are based at universities and they continue to assist with testing, development, and contribution of ideas and solutions. We have a regular seminar program in which challenges and their solutions are debated. The system integrates into a university or college through an application programming interface or API, which manages the data access and translates it to the form expected by the AutoScholar. The API is accessed in a closed loop between an authenticated user and the institution. So even though you receive AutoScholar functionality, all the information transfers respect the modern privacy protocols. Skipping forward, let's get into some functionality. In progression mapping, we determine the routes to graduation taken by our students. We design the curriculum as if it's one thing, but if you mine the student data, you'll find a crazy number of routes to final graduation. We want to do this to determine where the gatekeeper points are that limit our graduation rate. To create a progression map, we use these two axes, namely the number of students on the y-axis and the percentage of credits passed on the x. A node is a certain list of course combinations, and an edge is one semester. We start with a basis of 100 students entering the academic program, and after one semester, just 70 students have passed everything, and 30 students have passed some other combination of courses. After one more semester, this group of 70 minimum time students breaks down even further. Some students will still be on minimum time, and some other group will have passed some other combination of courses. So behind each node, we can imagine a combination of courses that a certain number of students have passed. At the end of each semester, each group further subdivides. We continue this route generation until we reach either graduation or fail out of all the students from the original 100. This then reveals all the progression routes taken by our students. In some cases, the map is quite extreme. You see that in chemical engineering, we're decimating our students, and after just 4 semesters or 2 years, the minimum time students are in the minority. We eventually have almost as many routes to graduation as there are students. We can then zoom into a particular section of the curriculum to look for bottlenecks with high fail rates, which are prerequisites to other courses. This really limits the graduation rate. To simplify the development, we then look at the minimum time route and among all the combinations, the specific courses that cause students to exit the minimum time group. We then know to direct more teaching resources to these gatekeeper courses. We can also timetable differently to allow some carrying of courses into subsequent years. This really helps increase the overall graduation rate. Here's another application. We can use the map to estimate what the academic program structure is without looking at the published curriculum and estimating it directly from the student data. In other words, we can estimate what the academic program structure is according to the perspective of the students. Here's one such example. In white is where the system has correctly identified the placement of courses in the curriculum. In yellow is where it got it wrong. It has estimated this course to be in the 3rd year when it's a 2nd year course, and this course to be in the 4th year when it's a 3rd year course, and these 2 courses to be in the 5th year, which doesn't really exist. Now let's look at the reasons for these errors. These seeming 5th year courses are only attempted then because they are prerequisited by this course, which is only taken in the 4th year. And we find it's only taken then because this is in fact prerequisited by this course, which has such a high failure rate that it's only ever attempted in the 3rd year of study. So these 4 errors are really just one error and one bottleneck. Now that we know this, we can direct more teaching resources to the second year course or timetable differently to allow for this course to be carried into the 3rd year. This can reduce the average graduation time from 5 years to 4 years. Now let's think about the coherence of our curriculum. In other words, which courses are building good foundations for the other courses. To understand this big table of numbers, we have running down the column here our 1st year courses, and running along this row the 2nd year courses. The numbers in the table are the Pearson R coefficients. We get these numbers by taking a given combination of courses. Let's say we take this 1st year maths course, and we want to know how it correlates with this 1st year chemistry, with the 2nd year chemistry course. We can do that by taking each student's combination of these 2 courses. So 1 point here, for example, will reflect the result in the maths course, and the other coordinate will be the result in the chemistry course. So 1 point is 1 student plotted at the position of their results. We do this for all students that have taken those 2 courses, and then the scatter will tell us the Pearson R coefficient, which is the number shown in the table. The closer the value is to 1, the better the correlation, like shown in the 2nd figure. And the worse the correlation, the greater the scatter, the closer the value will be to a 0. Looking at these values, we can see that this course, which is supposed to be Introduction to Chemical Engineering, has some of the weakest correlations with our 2nd year courses. So it's not introducing anything. On the other hand, if we look down at this course, which is a 2nd semester physics course, which is routinely thought of that should be dropped because why do chemical engineers need so much physics? This course has some of the highest correlations. And so this is possibly serving an important foundational role. So this method helps us make important curriculum decisions. Now let's look at predicting whether students will pass or fail. In this data set, we would like to create a model which will predict whether a student will pass or fail this course, Reactors 3, given the results in Reactors 2, Maths, Economics, and Psychology. This data has no obvious correlation. This is complicated and more like a scatter. However, using the decision trees method from machine learning, we can create a model which perfectly captures this data. According to this model, the best predictor of the Reactors 3 course is Reactors 2. If you have marks in this low range, you'll likely fail. If you have marks in this high range, you'll likely pass. And if you have marks in this middle range, it's not enough to look at just Reactors 2. You then also have to check your maths marks. And if you had passed first time, you'll likely pass, and failed first time, you'll likely fail. And it's important to note that this model has not been developed by any human intervention. No one's looked at the prerequisites and proposed this model. This model is entirely machine developed directly from the student data. What I especially like about these classification trees is that you can read directly on the model the coherence among the courses. It almost tells you which courses should be regarded as foundations for the course of interest. There are also many reports that can be auto-generated. There's a lot of other machine learning that you can do on the data. In some of our workshops, participants have said things like, I can write code or make models without writing code. One person has spoken about what he calls data democracy, which is a term that caught on in these sessions. And it means that now with better access to data and analysis methods, it unlocks a great deal of potential for understanding our students and our processes. Using some of our other machine learning and the concept of boosting, we are able to train some very high accuracy risk predictors, even in the high 90s. We also find that with interface design, we are able to influence student behavior very powerfully. For whatever reason, when a student can see their profile on their cell phone and it shows accurate data about them along with machine advice, they are frighteningly receptive to it. The system can auto-generate natural language messages to students about their progress and what's needed to improve. One has to be quite careful with the script design, or you can easily create self-fulfilling prophecies of doom. So by balancing the advice well and by combining with a bit of data with the advice, you have a powerful means of promoting student success. One concern I have is that the system almost makes life too easy. I've personally been in situations where staff realized that the AutoScholar was giving them the same decisions that they eventually arrived at after long discussion. These long discussions are useful and guided my own decision making, and we lose something when the automation makes things too easy. There's a bunch of other functionality I'm skipping through here. We do have a process in place. If you'd like to trial the AutoScholar at your institution, feel free to reach out. There's also a component which you can use to create other AutoScholar components. So at your institution, you obviously have some new methods that can be made accessible to others. And through our component builder, you can do this. You can also use the component builder for creating any data science or machine learning projects. The Modern Scholarship Seminar Series is where we have some active debates going. We have active participation from multiple institutions in different places in the world. Feel free to join in this discussion. Thanks kindly for listening.